Can you hear? Yeah, thank you. So we had a lot of discussion in the panel yesterday that moving towards to exascale, we have to run the applications at that scale efficiently. So how can we accelerate the HPC applications without changing the? So one way, we definitely have to come up with the better application algorithms, but how can we accelerate the applications with the middleware and hardware technology? So one way is, if you see HPC applications, MPI and OpenSHMEM applications, you can accelerate them through better middlewares with improved collective performance and better overlapping of the computation and communication. And by doing so, we can give the more CPU availability to the application. So in the same way, so we can accelerate the machine learning and deep learning applications, distributed machine learning and deep learning applications. So in the earlier talk, we had seen that it is very important to have a better communication between the machines for the better deep learning and machine learning applications. So if you see many of the deep learning frameworks like TensorFlow, Microsoft CNTK, Caffe, many of them are moved towards the HPC middlewares like MPI to for better internode communication. So what Mellanox came up with for this is a switch IB2. It's a smart switch. So it has a great features listed here. So better, it's a it's around less than 90 nanoseconds and better throughput. And apart from all these, it has a technology is called Sharp. With this technology, you can offload the MPI operations onto the network, and you can free the CPU for the computation part. So the network can compute the data as moving in the network. So the network is acting as a co-processor here. So these are some sample MPI Alreduce data. So if you see here, it is on the 128 nodes, one rank MPI rank per node. You can see a significant improvement in the latencies for the Alreduce. So with such a benefits, you can accelerate the applications which are heavy collective bound applications. So this is the micro benchmark, but if you profile the applications, you see that they can have a load imbalance and system noise. All these factors can contribute to a much more collective latencies, higher latencies. So these effects can be reduced with the in-network computing. So we'll see. So let's take a simple Alreduce. This is on the 4 nodes. The standard host-based approach is let's do a simple recursive doubling. So here my rank 1 process will send it. In the first step, it will send to 2, and it will get from 2, and it will compute the sum or some reduction operation. Once the result, it will send it to in the next step, it will send it to 3, and it will get the partial results from 3, and it will have the final result here. If you see here, the rank 1 has to participate in many steps. As the scale increases, the steps increases the logarithmic way. And if one is has to come to the network and check the data many times. So, but if one is if it is busy with some computation, so then the overall collective performance grade might affect significantly here. So this is this is the drawback with the host-based approaches. So now, what we did here in the Sharp technologies here. So all the end nodes, if you see here diagram, all my blue dots are tree end nodes. That is the compute nodes, and all red marks are here network switches. So here, all the end nodes, when they have to compute, they put their data into the network, and they are free to do compute on anything. So while data is moving inside the network and moving up to the network, so the switches, the switches can do the reduction operation, sum or max, any MPI reduction operation, and the tree root will have end results, and it can push down the data to the end nodes. So while doing all these operations, so the end nodes involvement is not there anymore. So they can just push the data, and they can do all the computation. They can freely participate in the computation. They just have to come back to the network only to get the final end results. So this is cool. So with this, you can avoid the system noises, and you can better overlap computation and communication. So this ultimately will give you a better performance of the applications. So here, so this is the tree-based aggregation protocol in the network. But it is not enough just having some computation capabilities in the switch, but you have to have more than that to support MPI communicators and ordering rules. So it should not interfere with one communicator computation with the other communicator. So we need a clear distinction between different groups and different ordering of the collectives. So all this, the Sharp has all these capabilities to do the very efficiently. So currently it has following collectives: barrier, reduce, and Alreduce and broadcast. It can do large variety of computations, and it can support different type of data types like integer, floating, 32-bit and 64-bit operations. If you see in detail Sharp tree, so the operations, the Sharp tree is a construct on your physical topology of the switch. So and it efficiently gets the tree based on your job where it allocated in the network, and within the fabric, it supports the multiple Sharp trees. Each tree can handle multiple outstanding Sharp operations. When you are talking about non-blocking collectives, you can push multiple operations from the same communicator into the network. At the same time, it will support multiple groups, large number of the groups. So that means many communicators in the MPI application can use this technology. The Sharp tree is just a logical construct over the physical topology of the fabric. Okay, within the Sharp tree, and the Sharp group is just a subset of the subtree. So let's take this example here. So here, this is my whole MPI job, and these are the first level switch involved here. Then this is my root switch. But let's say if you are creating a communicator just over these four with 4 end nodes, then your Sharp tree is just a subset. Your group tree is just subset of the bigger sharp tree here. So then the result just has to be computed here and get down here. It doesn't propagate all through the network. So let's focus. Focus on the sharp software here. So currently we have a latest release. The last week we made is version 1.2. It requires latest MOFED and switch IB to latest firmware, and it released with the latest HPCX 1.8 release. So sharp software presently delivered as a part of the HPCX package. So as I said, Sharp is part of the HPCX. I would like to give a brief overview of the HPCX. So HPCX it's a complete open MPI PGAS and OpenSHMEM UPC package. It pre-compile binaries, and it has a best software to leverage all the advantages or benefits with the Mellanox hardware. It supports both open source and commercial applications, so it gives the best out-of-box performance. So currently the package, this package has OpenMPI, Berkeley UPC, and UCX. So this is the Mellanox latest and greatest point-to-point library. So we have previous version of the point-to-point library MXM, and we have multiple collective accelerators. The collective library is called HCOLL, and we have a sharp software. We have KNUM for better intranode performance. Along with we have profiling tools and benchmarks. So how we integrated the Sharp with the HPCX? So if you take the MPI, so MPI is the current HPCX. The MPI collectives are taking advantage of the HCOLL library. HCOLL is a hierarchical collective Mellanox software. So it has a very efficient algorithm, MPI and OpenSHMEM collective algorithms. So now we directly integrated Sharp because Sharp has it has a certain set of it supports certain set of the collectives like Alreduce and Barrier and Bcast. So to make a full-fledged collective library, the HCOLL is integrated through Sharp. So all the Sharp supported collectives will go through the Sharp, and all remaining collectives will use the other way of other algorithms. So the Sharp library, so it will directly post the collective request or aggregation request to the InfiniBand network, and it will and get the results back. So the Sharp library, the Sharp, it has a easy to use API. Currently we have two set of APIs, high level API, it's very abstracted API, or if somebody wants to use very native, very native performance or native integration, they can go to the low level API where it deals with the Sharp network packet level details. So this is the architecture of the Sharp software. So this is my fabric. So here aggregation node, the switch is termed it as the aggregation node here. This is my compute nodes, and compute nodes are running multiple MPI ranks. So each node has a Sharp daemon, and there is a central place where both subnet manager and Sharp aggregation manager are running. So the aggregation manager, this is a piece of software which deals, which configures the Sharp, which allocates the resources for the MPI job. So whenever we spawn the MPI job on the compute nodes, so they request some resources like how many communicators you want to use the Sharp resource, how many outstanding operations, max outstanding operations you can push it to the network. So there are some resource allocation for each job. So when you launch the job, either the cluster resource manager like Slurm or LSF or native MPI launchers like MPI Run, so they talk to the aggregation manager, and the job will, so the MPI job gets the resources. Then the sharp daemon running on each node, they are the proxy for talking to the aggregation manager here. So software components, there are two libraries. So one is the libsharp and libsharp-call. So as I said earlier, so there are two level of APIs. So for each one, there is a corresponding library. And so the sharp requires the Daemons services, one on each compute node and one on the central place where OpenSM is running. And it has a bunch of benchmark scripts and utilities. And there is a public API. If anybody wants to integrate into MPI or any other framework, it's easy to integrate API. So sharp daemons, sharp AM, aggregation manager, it should run on the same node as a subnet manager. So this is the resource manager for the sharp. And each compute node runs a sharp daemon. This is the lightweight. So it's almost 0% CPU usage. It's involved only in the control path of the job. When you are actually running a collective, it do not involve in the MPI communication. So how to configure sharp? So when you have switch IB2, it is optional to enable the sharp or not. So how to enable? So when you're running the OpenSM in the configuration file, you can specify that sharp enable option. So and then run. Once you run that, you will, when you run the IBNet discover, you will see a special string in the output. This is the virtual interface that it's saying that Mellanox Mellanox aggregation node. So this indicates that the sharp is enabled at the fabric level. So and how to configure the aggregation manager? So once you run the subnet manager, so get the fabric LST file and copy into the fabric for the configuration folder, and and if you run your OpenSM with the GUID file, root GUID file, then copy that file. Otherwise, you need to physically locate what is the root of the fabric, then put that into a file and make a conf file. And once that is done, so it's a service, or there is a service scripts provided with the software. So you install the service scripts. So once that is done, you just start the service AM on AM. Similarly, on each compute node, you can start the you can install the sharp daemon service scripts, and you simply start that. So this is the system administrator does this. So once you up and running the cluster, so you do this once. So I will skip this. So once this is done, so with the HPCX software, so there are a couple of options to enable to request the sharp for MPI applications. So there is HCOLL enable sharp. So with this flag, you basically so you can request the sharp resources through the HPCX. So I'm not running this. So this is a sample run I took it. So I have a small demo I would like to show. So HPCX, so you can download it from the Mellanox website. So you get it for your installed MOFAD and OS. So once you're done, it's easy to use software. You just extract it. Once you extract it, you will have all pieces of softwares here: HCOLL, OpenMPI, UPC, OpenSHMEM, Sharp, and UCX, MXM. So it's once you init it just load the modules. So once you load it, so all the MPI environment is up and running here. So MPI run and MPI CC. So let's see. So is my openness. So in the OpenSM config file, the way to enable the Sharp is the Sharp enable to. Once you have this configure file, you just run OpenSM. Once you run this, you will get in the log, you see that Sharp is enabled. So once this is done, in the IBNet discover, you will see a So you will see that the switch is marked as a aggregation node now. So here I'm running on a 32 node. Oops. Yep, this is my switch. So here, so this is my 32 node cluster. So Jupyter 0012 0032, all are connected to a single switch, and all ports are connected to single switch, and it is a switch IB2. The Sharp is enabled here. So once this is done, so this is my head node. Here I am running OpenSM, and I prepared my Sharp aggregation manager conf file. Here I specified what is my fabric list file. This file is generated by OpenSM when you run it. So you just copy it into here, and the root GUID file. If you see this, so I have a one entry here. This is the root of my fabric, because I have only one switch. All 32 nodes are connected to here. But if it is a multi-level fabric, so then you have to specify the root of the fabric here. This will use it in a Sharp aggregation manager to correctly compute the Sharp trees. So once this is done, I just started my aggregation manager. So the log files will be here. So it has a one tree. So tree ID is configured, and it is ready to accept the job requests. So this is the Sharp aggregation manager runs on the central, head node. Then on each compute node, you need to start these service Sharp D service. These two are the administrator responsibility to set up. Once this is done, at the MPI level, MPI run, here I am running OSU micro benchmark. with the 32 nodes, I'm using one ppn because this map by node. So and this is my option to sharp enable HCOLL enable sharp. So here I disabled it now. So even though Fabric is configured with sharp, but this command line is this MPI application is not requesting the any sharp capabilities here. So this is my kind of latencies we got, 5 microsecond on 32 nodes, PPN1. So now let's see. So with the sharp, we reduced up to 2 microseconds on 32 on one switch scale. So it's more than 2x reduction in the Alreduce performance for the 4 bytes and 8 bytes. If at 256, it's even more. So as you scale out your Fabric, on thousands of nodes, so because there is no host involvement in the MPI collective communication, so all your reductions are happening in the network. So it's you see the very scalable collective performance. Yep. So that is a small demo to just to show the impact of the Sharp. Sharp API. So now Sharp we integrated with the HPCX, but it's not for HPCX, but it can be integrated with any MPI. So we currently integrated with, it's also integrated into MPitch. And as today's morning, Dr. Panda said, the MPitch team also is working on integrating it. So it is available in their next release. So not only MPI, so the target is for using it for other deep learning and machine learning frameworks. Like in the earlier presentation, we saw that DGX box, so where NVIDIA has a very nice inbox collective library called Nickel. So, but if you scale out, you need communication between the intra node also, intra machines. So it is expected to see Sharp will play a great role in such environments also. So the API, I quickly go through it, a couple of slides. So it supports different data types and different reduction operations, which mostly covers the MPI and OpenSHMEM data types and reduction operations. So the Sharp API is very simple. The high-level API, it has two set. It has control path API and data path API. And the control path API is like you create the job and create the communicator, destroy. Finalize the MPI job or destroy the communicator. So in such case, those calls will translate into a control path Sharp request. Like when at the time of MPI job creation, it has to create the Sharp tree. At the time of MPI communicator creation, it has to create a Sharp group. And in a similar way, you need to tear down those groups and trees when you done the operations on it. So in sample, in HPCX, this is the code flow translate into Sharp. So for example, MPI init. So there you initialize the HCOLL init. So that will translate into Sharp call init. So it means the Sharp will create the Sharp tree on the Fabric. So it's very simple API. You give you input a very minimum set of options like job ID to uniquely identify the Sharp job in the Fabric, and what hosts are participating in the Sharp, and what is the rank of my process, and And at the same way, during the finalize, the MPI finalize is translated into HCOLL finalize, that will translate into a sharp call finalize, that will tear down the sharp tree in the fabric. Similarly, the COM create, MPI COM create. So for each communicator, you need to have a sharp group in the fabric. So that will translate into a HCOLL create context, and that is translate into a COM init, sharp call COM init. So that creates a sharp group in the fabric. So similar way tear down. And it has a easy to use interface like MPI barrier and MPI Alreduce. It has a sharp call do barrier, and you specify the sharp communicator which returned in the previous API, and Alreduce you specify MPI kind of input, what is the root of the operation and source and destination, data type and length of the buffer, and what operation you want to perform. So it also has a non-blocking API. So this is very important, non-blocking API, because if you want to effectively utilize, you want to overlap communication and computation. So this the MPI standard introduced the non-blocking collectives so that you can initiate the collective and go back to the computation and come back for the result. So where the sharp is betterly suits for this features, because all the reduction operation is going in the network in the background while the MPI process is doing the computation. So a quick summary. So it's a scalable in-network computing, and it's easy to use. So there are a couple of steps for the system administrator, but once this is set up done, all applications can use the sharp feature with a on and off flag, and it has a easy to integrate API. It can integrate into HPC applications and deep learning and distributed deep learning and machine learning applications. Thank you.